All right, how's it going?
Good.
Good. How's PA2?
Good. Going good. Good.
So, excellent opportunity to ask final questions on PA2 before you turn it in tomorrow morning at H, or before, preferably. I'm probably not going to be around a lot on email tonight, so if you've got a burning question, this is the time.
Is there when we use Fget, is there a max number for sticks that you want us to?
Anything reasonable. So some people have noticed if you put in 25 gazillion, it misbehaves. I'm not going to do that. Right? I'm not going to play it with more than 100 sticks probably. So integers can only go up to 2 billion. And if you put in a number bigger than that, scanf may convert it to some weird looking number, often negative. So don't worry about that.
Okay.
I'll test your program pretty reasonably, right? I'm going to run it with an invalid command line argument. So I'm going to say stick haha, and it should yell at me and exit. I'll say stick, it'll ask me how many sticks, I'll say haha, it should exit. I'll also try that with negative numbers, should do the same thing, yell at me and exit. And then I'll try stick 20 and play the game with 20. I'll try stick, it'll ask me how many sticks, I'll say 20 or 30, I'll play the game. All of that should work. Okay. When it asks me how many sticks to take, I'll try putting in a number bigger than 3, a number smaller than 1, things that aren't numbers like haha, and I'll try that at least 3 or 4 times and make sure it keeps trying. And then I'll play the game in a way that the computer should win. I'll play the game in a way that I should win and make sure that those things happen. And I'll look at your code, I'll see how it's organized, I'll see that it's well commented, I'll see that it has your name in it at the top. And that's pretty much what I'm going to do for each submission, right? Well, I'm going to untar it, I'm going to unzip it, I'm going to untar it, I'm going to compile it, and then I'm going to do all of those things. So if you go through those tests and it looks like it works, you should be good for 100%.
If we wrote it in a bunch of separate functions, how do we submit all of those?
So let's talk about the submission, because that is sometimes tricky. So go into the directory where you have all your code, and you want to make a tar file first. So tar, I'm out of ink. So tar cvf, and I'm going to say don't call your tar file the same thing as your program, because you're just asking for a mishap. So if you're calling your program stick or stick2 or something like that, let's call your tar file something like programming assignment 2. You can call it whatever you like, but don't call it stick.c.tar, because if you forget the top tar, you'll lose your files. So tar cvf, name of the tar file, and then any files that you want included in that. So if it's just one program, stick.c, just say stick.c. If you modularize into different files, you can put all of those files in here. If you've got include files.h, you can put those in there. Anything you want to put into the archive. Okay. Typically, you don't include an executable program in an archive, but you can, right? But I'm only going to look at the source files, and I'm going to compile them myself. So go ahead and make that tar file, and then compress it with gzip. So gzip, and whatever you call that tar file. And that will give you a new version of this that ends with .gz, and then rename that. So move pa2.tar.gz to pa2.tgz. That's the file you want to actually upload. So now copy that file to your computer and then upload to Canvas. Make sense? Now, if you want to do the acid test and make sure that this all worked correctly, here's my suggestion. So download whatever the TGZ file was from Canvas, and download it somewhere new, right? Don't just download it to the same place that you already had this, because if the download fails, you're not going to notice. You're just going to see the old version. So move into a new directory on your machine, download the TGZ from Canvas, right? Copy to the Linux server, and then log into the Linux server and make yourself a new directory. Some directory that does not exist. Call it whatever you want. Okay? And then say copy that file that you just downloaded from Canvas and pushed over with, you know, WinSCP or SFTP or whatever your favorite tool is. Copy that file into this new directory. Bless you. And then change your directory to that new directory. And do an ls. And there should only be one thing in there, and that's pa2.tgz. And the idea is you're going to do all of the testing of this in some totally different area from where your actual code is. Right? Don't start trying to unpack this where you've got your only copy of the code. Right? So make a new directory, copy your TGZ file into there, go into that there directory, make sure it's the only thing in there, and then reverse this process. So gunzip pa2.tgz. That should leave you a pa2.tar, and then say tar xvf pa2.tar. And now you should have in your directory, in addition to pa2.tar, all of these files that you put into the tar archive. So then do your gcc-o, build your executable, and then run your executable program and make sure it still compiles and runs. And if you can get to that and it's running your program and it's the same program that you thought it was, you're probably perfectly fine on the submission. Right? And this is exactly what I do when I'm grading. I download the TGZ, I push it over to the Linux server, make a working directory, etc., etc. So the two most common things that I'm hearing from people that are tripping people up. So here's a scanf statement to take the first command line argument, convert it to an integer, and store it in numsticks. Okay. How do I know if this actually found an integer or if it might have found something like haha? How can I tell?
Set a variable equal to scanf, and then check to make sure its value comes out as 1.
That is the only way to tell, right? So have some variable, like stat, set it equal to that return value, and then see if stat is exactly 1. If it is, you got an integer. If it's not, you don't have an integer. You cannot tell this by looking at numsticks. And in fact, if stat is not equal to 1, you should not do anything with numsticks, because numsticks is basically random. Or if you initialize it, it's whatever value you initialized it to. But it has nothing to do with argv bracket 1 unless stat's equal to 1. Okay, that's the first point. If this does not return a 1, numsticks has nothing to do with argv bracket 1. Right, scanf does not touch numsticks. Okay, the other issue Could I ever use this as the first line of my main program? This statement.
No,
Why not?
if there isn't an argv,
If there isn't an argv1, I'll get a segmentation error. You never, ever, ever want to try to scan argv bracket 1 unless you first check argc. Right? So first I would say if argc equals 2, then I can go ahead and I can look at argv bracket 1. But if the first thing you do in your main program is say, well, let's see what argv1 looks like first of all, right? If there's no command line argument after the program name, that'll throw a seg fault. Okay, so those are the two most common things I'm seeing, not looking at the return value to see if it converted to an integer and trying to convert argv1 before you know if it exists. Right? And if argc is equal to 1, this is null, and it'll seg fault. And I'm seeing almost no issues from people with actually playing the game, with actually using the strategy to figure out how to take the right number of sticks. All of that seems to be rock solid. Most of the issues seem to be in dealing with arguments. Yeah?
What's the right command to exit the program?
If it's the main program, you can just return. If you declared integer main, then you have to say return some number. And you just return 0. It doesn't really matter. I'm not going to do anything with it. If you're in a function other than main and you want to return, you can use exit. Or you can set a value on the return of whatever function you're in and have main pick up that value and exit with a return.
So if I'm in a separate function and I exit, does it exit out of the thing completely?
It should exit out of the thing completely. But let's try this. And to use exit, you have to include standard lib. So we'll just print out a message at the end of each function. And main should call sub1 should call sub2, and sub2 should exit immediately without ever printing any of these things. Oh, it really didn't like that. That's just, I think that's all just prototyping. All right, so that just exits. I think I did.
No, I just said I did.
Oh, okay, okay. Whereas if we do return, then it returns from sub2, but it continues executing sub1, and then it continues executing main. So, cool, that's a good test. Okay, yeah. Cool. Other questions? All right, so let's talk about debugging. So you're trying to write a program to do something. We're going to pick on a sort today. We're going to try to sort a bunch of numbers. But whatever it is you're trying to do, play a stick picking game, whatever, you're writing your C code. Somewhere you have an algorithm. It might be a flow chart written on paper. It might be something in your head. It might be pseudocode on a board. But somewhere you've got some kind of idea of an algorithm that you're trying to implement. And you're trying to take the steps of that algorithm and convert them into C code. And you do that, and you try to compile it. And if there's problems with the syntax, the compiler will tell you. and has nothing to do with your algorithm yet, right? It's just figuring out the language that the C compiler likes. So you work through those, you get rid of your errors and your warnings, and your code compiles, and now you're ready to execute it. And a few things can happen when you run your program. First thing that might happen is it works perfectly. Okay, that's awesome. Then you're done, maybe. Next thing that can happen is it blows up. It gives you a seg fault. Okay, or it runs and it exits normally, but it's not doing the right thing. It's not picking the right number of sticks, and the computer keeps losing. Or it's supposed to exit when you type something in that's wrong and it doesn't exit, right? Or maybe it just doesn't seem to do anything. You hit the enter key and it just sits there and it stares at you and it's running forever but not doing anything. Or maybe it's spewing output off your screen like crazy and it's printing a gazillion matchsticks, right? But somewhere you're observing something that's different from what you wanted to observe, okay? So that's the beginning of identifying a bug. This is what the program should do. This is what it's doing instead. Okay, so that's your only clue as to what's going wrong. It should print out the number of sticks, but my whole screen is filled with matchsticks. Okay, so next challenge is try to figure out where in your code this problematic behavior is happening. So if you have this happen, you're writing your program and it's supposed to print out 10 sticks and it starts filling your screen, how do you figure out what's going on? What do you do to try to debug this typically? Say again? Try to print it, right? Number one go-to for debugging is print statements, right? We can do two things with print statements. One, we can tell where we are in our program. We can say, I'm about to call pick, right? I'm about to call start. And number two, we can look at the values of variables. I just came back from my call to start, numsticks is equal to, and we can print out the value in numsticks. And we can see that it's 87 billion instead of 20, right? What else do you do when you're trying to debug?
Well, you can also modularize.
Mm-hmm. Okay, so you can try to break your code into pieces, right? And then what, like test each piece individually maybe?
Yeah.
So you've got a function that's supposed to tell you how many sticks you're playing with, right? Pull that out, put a simple main program around it, and just exercise that function.
Just from the point at which things start not working.
Mm-hmm. Okay, cool. So, and this is especially helpful if you've already modularized your code, right? You have these smaller pieces to check, and you can say this unit is working, this unit's not working, this unit's not working, right? So that's another approach. Sometimes I find students just staring at their code, right? You can stare at it for hours. You can print it out and paste it on the wall and stare at it. Sometimes that works, right? Sometimes suddenly you'll see something in there. But a lot of times it's more just kind of a taking a breath exercise and collecting yourself. Sometimes you play computer, right? You look at your code and you got a sheet of paper and you say, okay, here I say size equals 0, so you write down size and you write a 0 next to it. And here I say if size is bigger than 0, and you say, yep, size is not bigger than 0, so I'll skip this. And you try to mimic what the computer is going to do on your code and get to a point where you can see that it's doing something different from what you want. So a lot of these things can be automated for us, okay? And so we're going to talk about ways to debug a C program using a tool called GDB. That's the GNU debugger. And GDB will sort of do for us the task of putting in print statements to tell where we are, to look at the values of variables. We can also change the values of variables. We can also say, I think this section of code is fine, but I really want to know what's going on in that section of code. and we can ask it to let us know when it's about to execute that section of code, and then we can start looking at that line by line, see what the variables are, and so on and so forth. So it will do all these, it will not do these for us, but it will make it reasonable to do all of these things. So this is GDB, a new debugger. It comes with Linux by default. Most systems have some sort of debugger, and the way these debuggers work is pretty similar from one system to another. So if you took 270, and you remember MPLab, right, that had a debugger in it. You could take your code and you could step through it one line at a time. You could examine the values of registers in the bottom. You could set up stimulators, sorry for the bad memories. You could set up stimulators to change the values of input pins and so on and so forth. Same idea as GDB, okay? GDB is pretty standardized across different Unix systems, and it also understands things like C syntax and C code and assembly language and other things. So it's it works well with debugging code. So before we can use GDB, we need to recompile our code with a switch. And the purpose of the switch is to say, when you compile this code, I want you to include information that's useful for GDB. So if you have a program written in C, and it says something like, you know, size equals size plus 1, and you've got some comments in there and stuff like that, all that stuff disappears when you compile and link. When you get an executable program, there's no comments inside. There's no variable names inside, right? Your variable that you call total number of sticks is just memory location 7FF31625, right? And if you're trying to debug your program and you want to know the value of total number of sticks, you got to know where that variable is stored. So we put in this switch when we compile, and it says keep all of this useful information. Variable names, comments, line numbers, all that sort of stuff. And all you need is this one switch -G. So you can say GCC-G, that'll say include debugging information. And the rest of your compilation is the usual. So I'm going to pick on a program called sort.c. It's a bubble sort program. And normally I just compile it, GCC-O sort.c. I'm going to use a -G switch, and it's going to include debugging information. And then when you want to execute your program, you say GDB, followed by the name of the executable file. So if you didn't name an output and it's a.out, you'd say GDB a.out. So here's my bubble sort code. I put comments in the top so we can see that the comments survive. So I have a sort function called sort. It takes an array of integers and it takes the number of integers in that array. So that's just the prototype. My main program, I've got an array of 100 integers. I've got my string that I read input into called buffer. I've got some other integers. Size is going to be the size of my data array. It's going to be the number of things in my array that I'm trying to sort. So I print out a message here that says enter a number, and it says hit Control D when done. So let's talk about Control D for a minute, and we'll talk more about this later. But when I'm running this program, I'm typing in numbers. It doesn't know how many numbers I'm going to type in. I need some way to tell it I'm done typing in numbers. The usual way to do that is to have the user hit Control D. And Control D signals what we call end of file. It means there's no more input coming in. So if we look at fgets, right, fgets reads from a stream up to this many characters, stores it in an array. It returns a pointer to a character. We don't normally do anything with the return value from fgets, but it does return a value. And normally it's a pointer to whatever those characters are that we just read in. But fgets returns null if there's an error or when the end of the file occurs. So this is just something that fgets does. There's no reason that Control D should be associated with null. Control D is not null, it's actually ASCII code 4. But the way that fgets is written, if you say fgets and you ask the user to type something in and instead they hit Control D, fgets will return this value null, N-U-L-L. Right? And null is defined inside this include file. And it's actually a pointer to location 0. So I can tell if we're done entering input by calling fgets. Right? So this says call fgets, read up to 120 characters stored in buffer. And if it returns null, then I'm going to kick out of this while loop. Otherwise, if it returns something not null, I'm going to go ahead, use my scanf to convert that input into an integer. I'm going to store that integer into my data array. And I'm going to look at the return value from scanf. And if it was equal to 1, I'm going to say, okay, I've got another number, so I'll bump up my size variable. Otherwise, I'll print an error message and say this input is invalid. And then I'll just keep looping through this while loop until the person hits Control D and I get a null. So that's something that you'll see a lot and you'll write a lot this course, especially next course, as a way to indicate end of input. And we'll play with that in a second. So after entering this data, I'm going to print out a message that says how many numbers did you input, right? That's size. And then I'm going to call my sort routine. And sort should rearrange the data in this first argument, this array, from smallest to largest, right? And I have to tell it how many numbers I want to sort. And then I'm just going to make a simple for loop, and I'm just going to print out my data in order. And then the sort routine, how many people here remember bubble sorts from 121? Yay, bubble sorts. So very, very inefficient sort routine, but I don't care because it's just data and time. So basically go through your array and compare each number to the number after it. And if they're in the wrong order, swap those two elements in the array. So set a temporary equal to the first number, set the first number equal to the second, set the second equal to the saved value of the first. Switch them around. And each time I go through this inner loop, right, one number should end up in the correct position. Second time through, a second number should end up in the correct position. So if I do this a total of len times, all len numbers, right, every number in the array should end up sorted. So let me show you how this works, and I'm not too worried about the details of bubble sorting and so on. So let's compile this up, let's run it. So enter a number, I'll do a 5, I'll do a 7, I'll do a 2, a 3, and a 1. And now I'm going to hit Control D, and it tells me I got 5 numbers, it called sort, it printed out my sorted array, and there's my data. Right? I can make a file called data, so I've got some numbers in this file, and I can say sort less than data. And now instead of reading from my keyboard when I call fgets, it's going to read from this file. Well, what's going to happen after it reads the 22 and then I call fgets again? It's going to say you hit the end of the file, and fgets will return null. And it'll do the same thing as if I hit Control D there. So it reads in those 6 numbers and then it sorts them. So whether I'm going from a keyboard and I'm hitting Control D at the end, or I'm reading from a file and just hitting the end of that, makes no difference to the code. Just look at fget, see if it returns null. And if you've used fget C to read a single character, same idea, right? Fget C, when it hits the end of the file, it returns this special value, EOF. So if you make a loop that you're reading one character at a time, you take the return from fgetc, you see if it's equal to EOF. And that'll happen if you hit Control D, or if you're reading from a file and you get to the end of it. So we'll talk more about that when we have to actually use those, which I think will be the final programming assignment. All right, so one more detail. If you hit Control D and it's not the first thing on the line, it's not going to generate end of file. Okay? Control D only registers as end of file if it's the first thing on a line. If I already typed something on here and then I hit Control D, it's just sees an 8 and some other stuff after it. Okay, so don't lose a lot of time over that. All right, well, I got my program. I can say GDB sort to try to debug it, but the last line that it tells me here will say no debugging symbols found. Okay, so stop right there. If I try to debug this, it's not going to work very well because I did not compile it with the -G switch. Right, I compiled this by itself, and it tried to load in all this symbolic information, variable names, comments, all that stuff. Didn't find any of it. Okay, so when it says no debugging symbols found, just hit a Control D to get out of here and recompile. And you can put the -G switch pretty much anywhere, but don't put it right after -O, because -O has to be followed by the output name. I could put it right after GCC, I could put it right after sort, I can put it after sort.c. Doesn't make any difference. So I haven't tried this. So if I compile without the -G switch, my executable is 8,560 bytes. And it starts with elf, and it's got mostly gibberish inside. All right, if I compile with the G switch, it's 11,552 bytes. It's bigger. And if I look at my executable, it still starts with my elf. It's still a lot of gibberish, but guess what? Somewhere down in here, I'm going to see human readable stuff. Right, and there's more. So it's throwing some extra information into my executable. That'll be useful for debugging. Now I can just run this by saying sort, and it'll still run as usual. But if I decide to debug it, if I say GDB sort, the last line it says here is reading symbols from sort done. Okay, that tells me it's got debugging information available now. So let's debug this. So GDB, whatever your executable name is. All right, first command that's useful to know is list. So I can say list, and I can see my source code, which is pretty cool. And if I say list again, I'll see the next 10 lines of my source code. And if I say list again, I'll see the next 10 lines. And if I say list 1, it'll show me 10 lines starting from line 1. So you can look around, you can examine your code inside GDB. All right, next thing, if you just hit enter, it basically repeats your previous command. So if I just hit enter here, my previous command was list 1. If I hit enter, it says you must want to list some more. So it pretends I just typed in the command list, and it shows me the next 10 lines. And I can hit enter and see the next 10 and the next 10 and so on. And then if I try to list more lines after this, it tells me there's no line 46. My program only has 45 lines. All right, so there's the beginning of my program. Let's go ahead and start debugging. So how do you start debugging? You say start. Go figure. So start. And basically it does whatever initialization it needs, and then it stops before it actually executes any instructions. So it says there's a breakpoint at sort.c line 7. That's this opening curly bracket. So it's about to start executing my program at line 8. Well, line 8 doesn't actually have any executable instructions on it, right? Integer data bracket 100 does not compile into any kind of assembly language instruction. It's something that the compiler needs to know to say, hey, I've got to set aside 100 integers somewhere. It's going to be called data. Here's where I'll put it, and when the person asks to do something with data, it means this location in memory. But there's no code associated with that. Same with all of these declarations. The first real executable instruction will be down at line 12 where it says size equals 0. And it's converted that to something like, clear file register size or something equivalent to that. All right, so it's sitting at line 7, and it's not going to do anything really until it gets to line 12. So what we want to do first is just have this thing execute our program one line at a time. Okay, and so the instruction for that is next. Next says, go ahead and start running the program and stop when you get to the next line of my program. So this says, stop at the next line of the program. So if I say next, it tells me it's about to execute line 12. Okay, so it will always show you the line that's about to be executed. I can try to print the value of a variable right now, so we also have a command print. We can say print variable. And we can also just use the abbreviation P because we do a lot of printing of variables. So I can just say P size, and size is 32,000 something right now. Right? Why? Because I never initialized size. I said it's an integer, but I didn't give it a value. Same thing with num. What's num equal to? Who the heck knows? I don't know what that means. But num has not been initialized either. So I'm about to execute line 12, which says size equals 0. So let's say next. Okay, it's executed line 12. It's about to execute my print statement. So let's check size now. Size is equal to 0. What do you think data is equal to? This array of 100 integers. It is. What do you think's in the array? Gibberish. Right? Because we haven't initialized it. Now, if I call my sort routine and I pass it data and I say, show me what you're trying to sort, and I print data and I see this, right away I know what's going on, right? Because I didn't type these numbers in. It's like, okay, why are these numbers all crazy looking, right? And if I run this again and I print out data, it'll have different crazy numbers in there. Now, if you do this on OS X, chances are they'll all be 0. Different compiler does different things. All right, so data's crazy, that's okay, we haven't input anything yet. It's about to say print out, enter a number, control D when done. So let's go ahead and execute that statement. And I say next, and it didn't print anything. What the heck? I said print, enter a number, but I didn't see it actually print that. And now it's going to do an Fget. Okay, so this is a whole nother topic in itself. But doing input and output is fairly inefficient compared to all the things that computers do internally. Printing historically meant, moving a mechanical type head to the right position so that when you move it forward, it hits a ribbon covered with ink and it makes an imprint of, the letter E. And then moving it over again and turning it so when it hits the ink ribbon it makes the letter N and so on. Very inefficient. It's not that bad today, but it's still a lot less efficient displaying things on our screen than it is doing things in the CPU. So output is usually buffered, right? When you say print this message, it doesn't necessarily print at that point. It puts those characters into a buffer and it says, hey, we're going to print this at some point. But we may not do it right now. Because you may have other things that you want to print, and we'll buffer them all up, and then we'll print them all at once, right? Okay, so when does it decide to actually print? If you try to print too many things, eventually the buffer gets full, it'll dump it out and print all of it. If you print a new line, it will dump everything. If you try to do input, like this fget statement, it will dump the output buffer. Or if you call something called fflush, you can force it to dump the output buffer to flush it out. But the issue here is that I did not print a new line on that print statement. Why? Because when I run this, I wanted to say enter a number, colon, and I wanted to leave the cursor up there so I could type the number in next to the prompt, right? But that can mess you up in debugging because you're not seeing this output anymore. So here's what we're going to do, and you're going to do this a lot when you're debugging. I'm going to hit a Control D. It's going to say this process is still running. Do you really want to exit? I'll say yes. I'm going to go into my code, and I'm going to say, okay, I want a new line on here. So I'll go ahead and add that. I'll recompile. I'll re-debug. I'll restart. I'll do my next. I get down here where it's supposed to print out the statement. I'll say next by just hitting enter, because that means do the same instruction. Okay, now it printed out enter a number. So I'm right back where I was 30 seconds ago. Okay, this is how you get really good at working with the debugger, because a lot of times you have to repeat everything that you've done. That's okay. All right, so now what's it going to do when I say next? It's going to call fgets. It's going to wait for me to type something in, hit enter. It's going to store what I typed into buffer, and then fgets is going to return some value, and if it's not null, then the next thing it would do is go into my loop, which is going to be doing an scanf. So what is buffer equal to right now before I execute this statement? Buffer is a character array. What do you think's in there? Gibberish. There's buffer. So it's got 24 nulls, and then a hex FF, and a 265, and some JUUUUs, and some PJUUUUs, and who knows what this all means. It's random stuff. But we're about to execute this call to fgets, so let me say next. And it's just sitting here. Why is it just sitting here? It's waiting for input. It's inside fgets. All right, so I'm going to type in a number. What's our favorite number today? 6. I'm going to make it bigger. I'm going to do 67. All right, and I hit enter, and it comes back. And it's about to execute line 15, which means that fgets must not have returned null because it's down to this statement now. And if fgets had returned null, it would have skipped this whole while loop, and it would be down at line 20. All right, well, let's see what happened. Let's look at buffer. Guess what? Buffer starts with 67, followed by a new line, followed by a null terminator. That's your input. And I can look at buffer bracket 0, and it's got the number 54 inside, but it's telling me that's the ASCII code for the character 6. And let's look at buffer bracket 1. That's got the number 55. That's the ASCII code for a 7. And buffer 2 has got a 10. That's a new line. And buffer 3 has got a 0. That's the null terminator. There's your string. All this other stuff is still sitting inside buffer. Doesn't matter. Printf, scanf, anything that I do with this string is going to stop looking once it gets to this null terminator. So it doesn't matter that there's other stuff in there. These routines are never going to look at it. All right, so we're going to scan buffer with a %d. We're going to try to store it in our data array at location size. So let's look at size again. That's a 0. If we print data bracket 0, it's got crazy number. Right? So let's go ahead and say next, and this is going to return its value into status. Let's see what status is before we do this. It's another crazy number. So we'll say next, and we'll look at status here. Status is 1. What does that mean? Converted an integer, stored it. So it should be stored in data bracket 0. Let's take a look at data bracket 0. That's 67. So we're confirming that everything that we wanted to have happen is happening as expected, right? All right, if status equals 1, we should increment size, otherwise we'll say invalid input. And then we're going to go back to the top of this while loop. So right now, size is equal to 0. If I execute once, I can see it's about to increment size. I can let it do that. I can print size, and size is equal to 1. Now I can say next. I can type in my new number, which is -2. And I can step through all of this. And I can look at data bracket 1, and that's a -2. And I can go back and look at data bracket 0 and confirm that that's still 67, and size is equal to 2. Okay, so I believe that this part of the code is working fine. I want to go ahead and input a bunch of numbers. I don't want to go through this process another 5 or 6 times. I'd really like to go through all of this until I exit the while loop. So down here at line 23 is the next statement after I've finished all of this. So I'm going to use a command in GDB called break. And you can say break line number. And it means the following. If I say break 23, it means if I tell you to start continuing your run, right, not just one instruction, but to keep running until you get to a break point. In other words, stop when you get to line 23, or if the program finishes or you get an error, right? So instead of saying next, I'm going to say continue, which you can abbreviate CONT. And it's just going to keep running, and it's going to run as long as it takes. And when it gets to line 23, that's a breakpoint. It's going to come back to the debugger and say, what do you want to do now? So I say continue while it's waiting for another number, and it's waiting for another number, and I can put in an illegal number, and I can put in some more numbers, and I'm going to hit my Control D to signal the end of input from Fget. And bingo, I'm down at line 23. So now I can look at my variables. I can look at size, it's equal to 6. I can look at my data array. It's got 1, 2, 3, 4, 5, 6 good numbers in it, followed by gibberish. Now if that's not the case, if the 6th number is gibberish, or if the 7th number is a number that I entered but size is only equal to 6, right, I've got a problem. So you get out of here, you go back, and you step through more carefully, and you try to figure out where that problem happens. But this looks good, right? So it's about to print out data size colon and show me the data size. So I'll say next, and it printed out data size colon 6. All right, it's about to call my sort routine. Here's the last detail. If I say next, it's going to call sort, and then it's going to tell me I'm about to execute line 28. Right? Because next says basically execute until you get to the next line of my program. So all these function calls to fget, to printf, have basically done everything in the call and then come back to get our attention. They're step overs in the language of MPLab. So instead of saying next, we can say step. And this is what we call a step into. It says start executing the function, but immediately come back and ask me what I want to do. So since I want to actually debug the function sort, I'm going to say step. And now I'm inside my sort routine. Right? So it tells me sort in the beginning here. It tells me what the arguments to sort were. Some crazy number and then a length of 6. And now I'm sitting at line 36. So I can list my function sort. I said list sort. And here's how the function is declared. And here's the first executable line. So this is what it's about to execute. But we can take a look at our arguments. We can print out length, and it's equal to 6. We can print out nums, and it's this weird hexadecimal number. But it's a pointer to an integer. That means it's an array. So I can print nums bracket 0. I can print nums bracket 1. And that's the actual data in my array. So why is it this big, long, crazy number? That's the address in memory where my array is stored. All right, so you got the idea? right? It's an exercise in patience and sort of tracking what it should be doing and using these tools to see what it is doing. So we'll talk about this a lot throughout this course, and we'll use it a lot in 222, but that's kind of a first intro. I'll post a video on Canvas that I made a few years ago that summarizes some of this stuff, but mess around with it if you like. All right, I'll see you tomorrow.